let's say, in our example, that the position as a function of time is equal to 3.00 t squared minus 5.00 t minus 2.00 meters. We're going to figure out a bunch of things. Part A, we're going to figure out the velocity as a function of time. Part B, we're going to figure out, I'm sorry, no, we're not going to do that. We're going to do the position initial. In other words, at time t is equal to 0. For part B, we're going to figure out the velocity as a function of time. For part C, we're going to figure out the acceleration as a function of time. For part D, we're going to figure out the velocity at 2 seconds. For part E, we're going to figure out, actually we'll do position first, then we'll do position, then velocity, then acceleration, all at 2.00 seconds. Vandervoort. Let's start with figuring out the position initial. How do we do that?
You set time to 0.
Okay. Where do we do that?
Well, you just use the original equation. You just do, is it t squared or t to the third?
It's t squared.
Well, that would just be 0 on the.
Okay. So let's just put it in so you can see.
Okay.
3 times 0 squared.
And then minus 5 times 0 minus 2.
So the position at 0 seconds is equal to
Negative 2 meters.
-2.00 meters. Great. That's part A. Part B, the velocity as a function of time. Landon, how are we going to figure that out?
It's 6.00 t.
No, no. This is an answer. My question was, how are we going to figure that out?
Take the derivative of the position function.
So I'm going to take the derivative of position as a function of time. Okay. So we're going to take the derivative of 3t squared minus 5t minus 2. Go ahead.
Equals 6t minus 5.
That's your answer?
Yes.
Okay. See, this is, I don't like this. The two Kevins, I get issues with these. Because we got Huang and Zhang. It just doesn't do it for me. Kevin, Zhang, what's your middle name? That's what I thought. Huang, what's your middle name?
David.
David! We don't have any Davids in the room. You're David. We're set. So when I call on Kevin, that's not you, David. You got it? All right. Kevin. What's wrong with this answer? Sig figs. What else is wrong with this answer? Connie? Units. We need two different things. Dimensions and sig figs. 6.00 t minus 5.00 meters per second. Part C. How are we going to figure out the acceleration as a function of time? Anna?
You're going to take the derivative of that.
That.
So it would be dv over dt.
So the derivative of, what are we taking the derivative of?
The derivative of wait, what do you mean by that?
What's the expression we're going to take the derivative of? I like to be very clear.
Oh, the velocity.
Which is?
Which is 6t minus 5.
6t minus 5. The derivative of 6t minus 5 with respect to time might.
6.00 meters per second.
Very nice. So, what type of motion, Riku, is this?
Uniformly accelerated.
Notice this is uniformly accelerated motion because the acceleration equals a number. Remember, that's what UAM means. In fact, you should have at the very beginning been able to tell me that this was uniformly accelerated motion. Ryan, how? All right, let's do this. It's okay. We'll take a side No, there's not going to be enough space. We'll just do it over here. We're going to take a moment to do a side piece. We'll come back to finishing this problem, but I want to do this first. If we were to do the example, the position as a function of time equals 7.00 t cubed minus 4.00 meters, you should be able to tell me right away whether that is uniformly accelerated motion or not. Jay?
Is it not because the powers of t don't decrease one by one?
They decrease one at a time, right? So the first derivative is going to give you velocity. The second time you take the derivative is going to give you acceleration. So what's going to be left when we take this, the two derivatives of this? Ryan?
Of the example up there?
Sure. Let's do it.
It'll
So
be
let's do
equation.
dx dt. Give it to me.
21t squared.
And then this is equal to the velocity as a function of time. So then dv dt is equal to?
41t, or 42.
All right. That's okay. Meters per second squared, and that's the acceleration as a function of time, which is not UAM. So you could look at this one initially, because the highest power value is a 2, that makes it uniformly accelerated motion. Anything greater than that, it's not going to be uniformly accelerated motion. Coming back to here, what is the position at 2 seconds? Ciccarelli, how are we going to figure that out?
You use the equation where time is a function of x, which is 3t squared minus 5t times 2. So you substitute 2 in for
Great. So we get 3 times 2 squared minus 5 times 2 minus 2. Gives us, what's our number here? 0. So work it out to be 0. 4, 12. Our initial position is, in fact, 0 in our particular case. E, the velocity as a function of time. Minji, how do we do that?
Okay, so you use the second one, which is 6.0 t minus 5.0, and then for t you substitute 2.
So we get 6 times 2 minus 5, or 7.00 meters per second. And the last one, the acceleration at 2 seconds. The acceleration at 2 seconds. Landon, what do you need to do in order to get that?
You use the equation that you got for C. It's 6.00 meters per second. That's the equation.
Okay.
ddt.
So what's our acceleration then at 2 seconds?
6.00 meters per second. So
What's our acceleration at 3 seconds then?
same things.
Again, because this is uniformly accelerated motion, it's irrelevant what time we're talking about. The acceleration is constant throughout, and it is equal to 6.00 meters per second squared. It doesn't matter what time we are specifically